Welcome back to lecture 3. The topic for today is fluid statics 1. So this is also the part of the basic fluid mechanics that we have been doing in the last 2 lectures. To get started, one of the most important question is the variation of pressure with depth in a liquid. How does the pressure vary? So to be able to give a real feel, has any one of you done scuba diving? That you will observe that the pressure increases as then you go down. So compared to if you are at the upper surface than at the lower surface, at the lower depths the pressure will increase. The increasing water pressure with depths limits how deep a submarine can go. These are the two classical examples of the variation of pressure with depth in a liquid. Many of you might have observed this. For in this case, the crush depth of 2200 feet is for this submarine. So if the submarine goes below that, due to the pressure of the water above the submarine, the submarine can crush. So now the important question is, why does P increases with depth? This is a volume of liquid. As you can see, there are some layers on it. So this is one layer, right? This is one layer. So this means this particular layer will have to support the entire liquid that is above this layer, and the same is for this layer. So this means this layer will have to support this much plus this much. So this is how you can understand why does pressure increases with depth. This layer of fluid must support all the fluid that is above it. So this block, the one that is shown in yellow in color, shall be supporting all the blocks that are above it. That is why, and another way to see why the pressure should increase with the depth. One of the other important feature of pressure is that pressure is always perpendicular to the surface. This is very important. As you can see, if this is a surface, we have a perpendicular like this, on this surface like this, on this surface like this, on this surface like this. Here we have already indicated by the thick red arrows here. And the pressure does depend only on depth. We are going to see that. We will do some basic derivation later in this lecture, where you will see that the dependence of pressure is only on depth. This is very important to note. See, this is one of the animated examples which everybody of you must have encountered in your real life. So there is a tap and this is a tank with some holes in it or some stopper valve. The valves are here, here and here. So we start filling the water. Let's suppose water gets filled. If we open this one, this valve, you see the water trajectory is going to be something like this. Similarly, the one above it will have a trajectory like this. The third one will have a trajectory like this. What does it say? The distance that each one of them is covering is decreasing as the valve is going up. This means that the pressure increases with depth. Therefore, the speed of water leaking from the bottom hole is larger than the one at higher holes, because larger the pressure, larger the force, therefore higher the speed, in a layman's term. This is for you to understand the basic concepts of how this pressure system works. Now some definitions and applications. In fluid statics, as we have seen, there is no relative motion between the adjacent fluid layers. Therefore, the shear stress is 0, as we have already seen this in our previous lecture. So what can be acting on the fluid surface? So only pressure can be acting in that case on the fluid surface. There is no shear, only pressure forces. Gravity force acts on the fluid, and that is called the body force. So gravity force, when it acts on the body, it is defined as the body force. What are the applications of this particular thing that we are studying about pressure? We can know the pressure variation within a reservoir, so it find application in reservoir. We are also able to find forces on submerged surface. You will see many cases in real life where the surfaces are submerged. We are also able to find, using this principle, the tensile stress of pipe walls, and also we are going to see the buoyant forces, because buoyancy plays an important role in this. What actually is the motivation? The motivations are enormous. As an Indian, we know, we have all heard of Bhakra Nangal Dam. So the forces acting on the Bhakra Nangal Dam, this is one of the very important thing, and for you as a student, I would consider this as the biggest motivation in design of dams, for example. So the question is, what are the pressure forces behind the Bhakra Nangal Dam? If this is the first step towards any design, you need to determine the forces or the parameters that determine the stability. So this is what I have shown here, is the upstream face of the dam here, and if you see it, if you put it in the 2 dimension, this is what the Bhakra Nangal Dam looks like. Okay, so this one here, the crest thickness, this is the crest, this is only 9.1 meter, 9.1 meter. However, the base thickness is 191 meter. And why that happens? It's very simple to explain, that as you go deeper and deeper, so this represents the increasing water depth in this direction. So as you go deeper and deeper, the weight of the water that it needs to support increases. Therefore, the base to resist the force, the base of the dam needs to be larger. This is a very simple explanation why we have a smaller crest and the base thickness is very high. What do we need to know while studying about pressure? We need to know the variation of pressure with direction. We also need to know pressure variation with the location. Direction is, say, in what angle, theta for example, location is at what depth for example, and how are we able to calculate the total force on the submerged surface. Okay, so these are the 3 questions that we are going to answer today. So first we are going to see the Pascal's law, which is pressure variation with direction. Very simple. This element, a triangular element that is shown here, this is a fluid element. The length in x direction is delta x. This angle is theta here. In y direction the length is delta y, and delta is the length of this surface. What we say first, when we make a body diagram, we need to have the forces. So the body force is, of course, we talked about gravity, so it's going to be the weight. What is going to be the weight? Very simple, it's mass into m into g. The mass can be written as rho into volume, right? So assuming in z direction we have a unit length, so the area of this triangle is half into delta x into delta y, multiplied by 1 will give us volume. So the mass is going to be rho into g into volume. Okay, so this is the weight of the element. Now looking at the surface forces, there will be surface forces acting. What we have seen before, surface forces in case of fluid statics will be only due to the pressure. So pressure will exist force on all these 3 surfaces. So these 3, this one and this one are going to exert force on these surfaces. What is the magnitude? So if there is the force on this, the pressure is Ps, it will be acting on this side in a unit z direction. So it will be Ps into area, that is delta S into 1. Similarly, in x direction it is going to be Px if Px is the pressure acting in this direction, and multiplied by delta y into 1, and in this direction similarly it is going to be Py into delta x into 1, because we have assumed unit length in z direction. Force is given by mass into acceleration. Therefore, mass into acceleration, mass is rho into volume. So, delta x delta y by 2 into 1, because we have assumed unit, and Ax. This should be equal to 0, right? And the summation of the forces on this body in the y direction is going to be Px, this one delta y. There will be a component in this direction for Ps delta s, this will be given by Ps delta s sine theta. So this is this component here. If we also know that delta s sine theta is equivalent to delta y because of trigonometry, right? Therefore, if we put delta s sine theta as delta y here, we are going to get Px delta y minus Ps delta y. It's very obvious now that delta y and delta y should get cancelled if they are not equal to 0. This give us Px is equal to Ps. Okay, this indicates that pressure is independent of the direction, and this was one of the properties that we have seen in the beginning, that pressure depends only upon depth. There is no directional, if there is no directional influence on the variation of pressure. Great. So I'll erase all links so that you are able to follow that in much more detail. Okay, so then, as we said, we should also be able to understand the pressure variation with location. Okay, so the small element of, we assume a small element of fluid in pressure gradient with an arbitrary acceleration. We assume, that is what our assumption is. We define our axis as x in this direction. So this is the x direction, this is the y direction, and this is the z direction. We are assuming a mass of fluid in cubical format. This is the fluid element. So as we have done always, what we are going to do is we are going to write the forces, but first assume that at the center, so I am going to use the pen now, the pressure at the center is P. Therefore, this will now actually, we will be able to help in the derivation, and there is a uniform pressure gradient, that is what our assumption is. So we should be knowing the forces acting on the surface of the element. So if the pressure at the center is P, and then the pressure variation can be given in this direction as delta P by delta y. So this is pressure variation in y direction, and what is the length? This is y by 2. Okay, so in this direction it will be P minus delta P by delta y multiplied by delta y by 2. So this is going to be the P1, for example. Here P1 is P minus delta P by delta y into delta y by 2, and it should be multiplied by the area. This is anyways a 3-dimensional element, so this area, that is, it's going to is delta x into delta z. So this is the force on this side. Similarly, on the other side, if the pressure is P here, and the gradient in, if we are subtracting when we are going backwards, so it will be added when we are going in the forward direction, and delta x into delta z. Similarly, for this surface, this will be, because this is z direction, right? So it will be delta P delta z, and the same principle multiplied by delta z by 2 to have the total pressure at this surface, and overall multiplied by area. This will give us a force, and similarly in this direction as well, because we have assumed that the pressure increases in the upward direction. So while going down it should decrease. It's P minus delta P by delta Z into delta Z by 2 multiplied by delta X into delta Y. I think this now you should be able to write on your own these terms. So what the mass of the element is going to be? Very simple. The delta M is going to be density multiplied by volume. Volume is very simple, delta X into delta Y into delta Z. So we have now written most of the things in one of these directions, right? We can see we have assumed in the direction of Y, the same can be done in X also, but we are going to concentrate in one direction right now, Y, the variation of pressure in Y direction, for example. Okay. So as we have already written the forces here in all the four sides, we are going to do the force balance here. So as I said, I will try to erase, okay, so that you are able to. Great. So now we have to simplify the expression for the force acting on the element. Very simple. So in the Y direction, the force is going to be, this was the force, pressure force, minus this forces. This was acting in this side, and this force was acting from the right. So P and P can get cancelled. We will have the same in X, Y and Z. So I'll just erase this one. So the summation of delta Fy, I mean if you do this addition, it will be minus delta P by delta Y multiplied by the volume. Okay. Similarly, if we do, as I said, we can do the same in X direction. We are going to get delta P delta X multiplied by delta X delta Y delta Z. This is important, and we can also get the same thing in Z direction. So it's going to be minus delta P delta Z delta X delta Y delta Z. It's just the force that we have calculated, the differential force because of pressure gradient. Now we can write these forces in vectors, right? So if you see, the pressure can be written as delta P by delta X in I direction, delta P by delta Y in J direction, and delta P by delta Z in K direction. So the summation of all the forces here, summation of all the forces, because this delta Fy is in Y direction, Fx is in X direction, and Fz is in Z direction, we can write the total force. If you sum these three, 1, 2, 3, you are going to get this equation, which is minus of delta P delta X I cap, delta P delta Y J cap, delta P delta Z K cap multiplied by the volume. Okay. So delta Fs can be written as, we can write this entire term as del P. This is a standard mathematical notation, and we keep this delta X delta Y delta Z as it is. Now the surface forces acting on the element of fluid due to pressure gradient. So this is the surface forces acting on element of the fluid due to the pressure gradient. So what happens? Now we have to apply the Newton's second law. So in Z direction, if you see, there is weight acting which is balanced in the K direction. Weight can be written as gamma, gamma is rho g, and this is the volume. So weight is mass into gravity into, so mass can be written as volume into the rho. Since Z axis is vertical, the weight of this element can be written as, see there is a force so the net force will be the surface forces plus the weight. Since the weight is acting downward, we have assumed a negative sign here, and this should be equal to delta M into A. So net force delta F is the mass into acceleration. We are doing just the Newton's second law here. Okay. So mass, as we already seen, is rho into delta X into delta Y into delta Z. This should be rho. This is mass of the element of the fluid. So, so the net force, because there is no acceleration, so the net force that has come to be delta P, delta x, delta y, delta z minus delta gamma. This is the weight, and this is the surface pressure forces, this is the weight, and this you will see this is acceleration, mass into acceleration, right. This is surface force, this is body force. Okay, very good. So now substitute into Newton's second law. If you see, we can get delta x, delta y, delta z cancelled from everywhere. So the final equation, so that you are able to see, I will erase all ink here, will be, right. So this is the general equation of motion for fluid with no shearing stress. This is very, very important equation, you should remember this. Great. Now as you see this equation here, minus delta P minus gamma K is equal to rho into A. One of the special cases is when the fluid is at rest, right. So in case of fluid at rest, the acceleration should be 0, and if we put A is equal to 0 in the previous equation, we can get delta P plus gamma K, this is the direction, okay, is equal to 0. Or if we write in component form, we can write delta P, because this is z direction, right. So in x direction there is only pressure, so delta P by delta x is equal to 0, delta P by delta y, and but in z direction it will be delta P by delta z is equal to minus gamma. Okay. In horizontal plane the pressure, so what does it mean? In horizontal plane the pressure does not change and varies only with depth as written by ordinary differential equation. So in case of no acceleration, there will be no pressure variation, okay, in x and y direction, only in z. So this equation in z direction can be written as dp dz minus gamma. Now one of the important thing is gamma may or may not be constant, right, and that is what we are going to see next. What are the two things that could make specific weight gamma vary in a fluid? That is very simple, because gamma you already know. Gamma is written as rho into g. So the two things are, if the change in density is changing or if the gravity is changing, right. There these two, I mean that can happen if you go to higher elevations, both can be affected, the density, gravity. If you go on from one latitude to the other, you might have read from your physics class that if you go to some place, some other place on earth, gravity might be a little different, not very different from, but we must consider all those cases, okay. So if we can write the previous equation, where the previous equation was what, dp by dz is equal to minus gamma. So this is what we exactly written, we have took dz on this side. Let's assume that the specific weight is constant, and this happens for this type of fluid, which is incompressible fluid. So rho is constant, and under assumption of gravity also does not change. This type of fluid is called incompressible fluid. Okay, we will be dealing with incompressible fluid throughout this course. So if it is incompressible fluid, we can simply integrate from P1 to P2 and from Z1 to Z2, because gamma is constant, we can take this out of the integration, and we can simply write P2 minus P1 plus minus gamma is equal to minus gamma Z2 minus Z1. So rearranging will give this one, P1 by gamma plus Z1 is equal to P2 by gamma plus Z2. Great. So this is called piezometric head, and this head is constant in a static incompressible fluid. That is one important take from this slide, okay. An important question is, how do we measure atmospheric pressure? One of the simplest devices, the barometers. See, what happens is that the column of liquid is held up by the pressure of the liquid in the tank. Near the surface, this pressure is atmospheric pressure. So, the atmosphere holds the liquid up. So, this this liquid is being supported by the atmospheric pressure. This is an inverted closed tube filled with a liquid. Okay. So, this is the barometer. This is the principle of working of barometers. Now, a simple question is, what is the local atmospheric pressure when R is 750 millimeters of Hg? This is R. We are just going to see, we have given the density of rho to density of water is 13.6, and we have assumed incompressible fluid constant rho. So, we are going to see how it works. Okay. So, this is 0.1 here and this is 0.2 here. So, we have seen this equation, piezometric head is constant. So, we can also write, let me erase this one, P1 is equal to P2 plus gamma Hg into Z2 minus Z1. Okay. We are putting this piezometric head equation between points 1 and point 2, and we want to calculate the pressure at P1. P2 is atmospheric pressure. So, atmospheric pressure we assume gauge pressure, that can be assumed 0, okay, that you have read in fluid mechanics. So, pressure at point 1 will be gamma Hg into R, because Z2 minus Z1 we have seen was R. If you just go back here, this P2 minus P1 Z2 minus Z1, this is 0.2, right. So, this Z2 minus Z1 is R. So, gamma Hg, and gamma Hg can be written as specific weight of Hg into gamma water, right. So, pressure will be S Hg gamma into R. On calculation, it is going to give almost 100,000 Pascal. So, this is one example as well of calculating the pressure P1, but this is also indicating how this barometer system works. Good. Now, we must also be a little aware about the pressure variations in a compressible fluid. So, there are two processes. One is perfect gas at constant temperature, isothermal, that we have been seeing till now. Secondly, perfect gas with constant temperature gradient, and actually you should try this at home. We are not going to cover this because in working this is the derivation is same as isothermal, with different, the way it works is the same. So, you should try this at home after watching this lecture. Now, we are going to do perfect gas at constant temperature, that is isothermal process. We start with the same old equation, dP is equal to minus gamma dz, okay, and where gamma is rho into g, where p is a function of, where the rho is a function of p, okay. So, because in gas it is PV is equal to nRT, that is the thumb rule for isothermal. So, rho can be written as N molecular mass of the gas divided by volume, or in other terms we can write it as P m gas by RT, where m gas is the molecular mass which we have seen in lecture number 1. So, dP will be minus gamma dz. So, this is minus gamma, right, correct, because we have already seen here, we just multiplied the density with g here. So, now we start simply integrating from P1 to P2 and Z1 to Z2, simple integration, and if you integrate this we are going to get, because it is dP by P, so that becomes ln P2 by P1, and dz is a simple integration yielding Z2 minus Z1. So, the pressure at point 2 in a constant temperature will be given as P1 e to the power minus m gas g RT Z2 minus Z1. So, in case of constant temperature isothermal, the perfect gas, the pressure variation will be like this. It's a very simple derivation, but a little more intriguing than the one that we did before for pressure variation within the liquid, where we got simply piezometric height. Good. Pressure measurement, the devices we have discussed one already, barometers. There are manometers, a standard manometer or a differential manometer, and the pressure transducers. This is out of the scope. You must have already done it in your fluid mechanics class, probably in your second year. So what does barometers do? Barometers measure the atmospheric pressure. Manometers, this standard manometer measures the pressure relative to the atmosphere. Differential, the pressure, it measures the pressure difference between 2 points. Good. So standard manometers, what is the pressure? So how it works is very simple example. So what is, if we are asked what is the pressure at A given the height, okay? More importantly, we should mention what is the gauge pressure, because gauge means we are not counting the atmospheric pressure. So P can be written as simply gamma into H, right? So pressure in water distribution system, for example, commonly varies between 175 to 700 kilopascals, right? So how high would the water rise in a manometer connected to a pipe containing water at 500 kilopascal? So the question actually here is, if we want to measure the pressure in a water distribution system, what will this height h in a manometer be? We are already told that the pressure variation in a distribution system varies between 175 to 700. In this example, they have asked us, we choose 500 kilopascal. So very simple equation, we substitute P, pressure is given, gamma we know, so H can be written as P by gamma. P is 500,000 pascal divided by gamma is 9800 Newton per meter square. So this will give the height 51 meters of water will rise in the manometer that has water in it. That is why, see, 51 meter is too high. So that is why this is the reason of using denser liquids like mercury. The height to which it will rise will be much less compared to, we simply, if you want to calculate, you can divide it by 13.6. so it will be something like around less than 4 meters or something. Yeah, good. So yeah, why is this a reasonable pressure? Yeah, I mean, this is the reasonable pressure. I think you think about it, we can discuss that in the forum. Another example for a differential manometer. So find the gauge pressure in the center of the sphere. So this is not a differential, so we are going to measure the high pressures. So find the gauge pressure in the center of the sphere here. The sphere contains fluid up till here with gamma 1 density, and the manometer contains fluid with density gamma 2. Okay, so we have to find pressure here. So this is point 1, we assume point 2 here, and we assume point 3 here, the center. So what do we know? We know that pressure at 1 is 0 because this is exposed to atmosphere. We have to use statics to find the other pressures here. Okay. So P1, so if the pressure at here it is P1 plus H1, because the same fluid, the pressure is increasing its direction, multiplied by the density, this is the pressure H1 gamma 2. So now we are going up by how much? H2. If you want to go to the center, we are going up. So minus H2 gamma 1 should be equal to P3. So we have found out P3 is equal to P1 plus H1 gamma 2 minus H2 gamma 1, right? So we know P1, that is 0, we know H1, we know gamma 2, we know H2, we know gamma 1, so we can easily find out P3. For small h, for small h1, this one, we use fluid with high density, okay, because in reality the atmospheric pressure must be taken into account, P1, okay. So we generally use mercury in manometers. Okay, good. So I think we will start with this particular slide in our next lecture and talk about differential manometers. Thank you so much.